Welcome back to Mastering C++20 Features. In this lecture, we will understand about the restrictions and requirements on a legal coroutine. Until now, you have understood how to create a simple coroutine, what are the basic requirements on the return type of a coroutine, how the coroutine could be resumed by accessing the coroutine handle encapsulated within the return type, and how to query if the coroutine has finished execution. But before we move further on to understand coroutines in more details, we should understand the basic restrictions on coroutines and understand different ways in which coroutine could be used. The restrictions on coroutines are pretty straightforward. Coroutines cannot use variadic arguments, they cannot be constexpr or consteval functions, they cannot have auto or decal type auto return types. This is because the compiler cannot deduce the return type with co-await, co-return or co-yield expressions. However, auto with trailing return type is still valid for coroutines. Main function cannot be a coroutine. Coroutines cannot be constructors and destructors. And as mentioned in the introductory lectures, coroutines cannot have regular return statement. Instead, we should use co-return to mark the end of a coroutine execution. At the bottom of this slide, you can find the link to CPP reference page that has a couple of lines on restrictions on coroutines. Now let's see all the scenarios with simple example and look at compiler error if we attempt to violate the above restrictions. Let me switch to the editor. In this file, I have coroutines that violates the restrictions mentioned in the previous slides. Therefore, none of the coroutines compile. Let's check each scenario one by one. The first example is a coroutine with variadic arguments. Note the presence of three dots here in function foo's argument list, which represents a variadic argument. If I try to compile the code now, I get a compilation error. The compilation error reads as cannot instantiate coroutine traits for the coroutine foo. This is because of the presence of variadic arguments in coroutines. If I change the variadic arguments in the coroutine to a template parameter pack, it will compile. It can be done simply by adding the auto keyword, and at the end of variadic parameter, I simply need to name the arguments. Now if I compile the code, it compiles. Next example is of a constexpr coroutine. If I try to compile this coroutine again, we see the compiler error. No return statement in constexpr function returning non-void. And similarly, if I replace constexpr with consteval, by the way, consteval is also a new keyword in C++20, and the aim of consteval is to guarantee compile time evaluation. But now if I compile the coroutine with consteval specifier, we get a similar error as previously in the constexpr case. I'll comment this again. The fourth example is the coroutine with auto return type. Let me clear the console here. Here, the coroutine has an auto return type and it doesn't specify the return object explicitly. But as stated in the lecture, this is also an error. And here we get the compilation error. Co-await cannot be used in a function with reduced return type. But if I change this to a trailing return type and specify the return object in the trailing return type, the code compiles again. And the fifth scenario is coroutines as constructors and destructors. So here I have the struct bar with constructors and destructors having co-await and co-return statements respectively. If I uncomment the default constructor, which has co-yield statement, and try to compile the code again, I get the error, co-yield cannot be used in constructor. Similarly, if I uncomment the destructor with co-return statement within its body, I get the error, co-return cannot be used in a destructor. The compilers are pretty smart. Now finally, the main function. In the main function, I have co-await, co-return, and co-yield statements. If I uncomment the code, Let me clear the console once more. Now if I try to compile the code once again, I get similar errors as previously. That is, co-await cannot be used in main function, co-return cannot be used in main function, and co-yield cannot be used in the main function. Now let's look at what a legal coroutine can be. A legal coroutine can be a freestanding function, which we have already seen, a member function of a class. In fact, it can be a virtual function in a polymorphic class. It can be a lambda expression. It can be a static function, that is a freestanding static coroutine as well as a static member of a class. Let's look at some examples in the editor that I've already prepared for this lecture. On top of the file, we can see a class object foo with a coroutine as member function in line number 8. In the next line, that is line number 11, there's a coroutine called static member coro, which has the static specifier. Therefore, this coroutine is a static member of this class. In the next section within the file, the class base has a virtual member function called virtual coro. And note, this coroutine is a pure virtual function. In fact, the compiler will not be able to deduce if the pure virtual function is a coroutine because it doesn't see the presence of co-await, co-yield or co-return statement here. Therefore, compiler treats this as a normal function which is declared as pure virtual function. Next, the struct derived publicly derives from base and overrides the coroutine virtual coro, and therefore this coroutine is a overridden function in the derived class. In the next section, the coroutine is declared as lambda expression. Note, without the trailing return type, this expression doesn't compile as it falls under the category of coroutine with deduced return type, which is illegal. And finally, a freestanding coroutine declared with the static specifier in line number 49. That was all for this lecture. I am uploading the files with the lecture and encourage you to get creative and experiment with the code. Thank you for watching the lecture and see you in the next lecture. Goodbye.